Alright guys, perturbation theory. You have, conceptually you can think of this as you have your normal function like this, very nice, then suddenly you introduce a field. You introduce a field that has some sort of force acting in that field, maybe some sort of electric field that does this. Your resulting perturbed wave function will be affected everywhere where this field or this force somehow interacts with your original wave function. So where it's zero, the force has no effect. Let's extend our wave function here. Where it's maximum, it's going to have the most effect right here. So least force effect, most effect. So what you're doing is, in perturbation theory, it's kind of like using the harmonic oscillator or rigid rotor or hydrogen atom approximations. What you do is it is an approximation using an exact solution, so one of these three exact solutions, or any other. You use these exact solutions plus the added effect of a small term from some sort of force, maybe. This means that you can rewrite the total Hamiltonian as the sum of the zero order original Hamiltonian, that's what this knot denotes, plus the first order perturbation denoted by this prime, or 1. That's what this notation means. It denotes a first order perturbation. So, simple enough. We're just combining to our original wave function some sort of new wave function. Now this makes sense, right? Because, looking at our visual, when we have our, let's make sure this is obvious. This is our bold wave function, right? And it's doing its stuff. But then this perturbation comes in. So to find the result, it's going to be additive, right? At least it can be additive. It could be negative. But that's the effect that we're trying to find. But we still have to add that effect, so that's why this is positive. Similarly, the true potential, is going to be equal to your exact solution, your original exact solution. In this case, we're doing a harmonic oscillator, plus your perturbing operator, your perturbing potential function, which was also a first order perturbation, as denoted by the prime. This means that the energy can also be rewritten. You see this pattern? You see this pattern where it's original plus effect, original plus effect. Your original energy will equal your exact energy plus the effect. Same level, same energy level here, but this is first order perturbation. What does this look like? This energy will look like, it's very intuitive. It's the integral of your original wave function, but with the perturbing operator acting on it. And this makes sense, right? Because you have your original exact wave function. If I can zoom out here, here's your zoom, original wave function, and then this perturbing operator is acting on it. Perturbing operator with some force F acting on your function sign. So that's the perturbation theory. There's a type of perturbation theory approximation known as the Hartree-Fock approximation. Now this solves the energy for multi-electron systems. using a single electron wave function product. Right, so what does this mean? Say you have some function of r1 and r2, and these are vectors. Right, so these are distances with some magnitude or some direction. These products that make up this wave function, they describe electron orbital spatial functions. Right? That's given. This just means here's my electron 1 in this place, and electron 2 is in this place. Hartree-Fock uses an effective potential, which describes your orbitals. This effective potential is going to be what you sum up to solve for the energy of a multi-electron. You will be finding the interactions between all the electrons. So for the first electron, the interaction occurs between R2 space and R1 space. So the operator is going to be 1 over R12, where R12 is equal to R1, or rather, doesn't matter, because it's the absolute, R2 minus R1. What this looks like in the, so if you can imagine, this is going to be your F. Once you put in your potential, effective, your new Hamiltonian will look something like this. You're going to have your kinetic, as always, that's fine. Then you have the interaction of your one electron plus this first effective. And what you do is you repeat this process for all electrons, for all electron interactions. So you can envision doing this again for 2. So this would change to the 2. Imagine this changes to V2 effective for electron 2, and then these change to 1 and 1. This stays the same, 1 and 1. Using this Hamiltonian, you get your orbital energy. So that's fun, and you can use that for other things, which we'll talk about. There's a problem, though. Like most approximations, it's not perfect. And the reason why is that Hartree-Fock does not account for correlation energy. And correlation energy is nothing more than the true energy minus the approximated energy. And with this, you can use density functional theory. This has never been more than just a definitional question, so I won't go into this. I can if you want me to. I can add more to this later, but right now I'm going to skip over this part. So what did we learn? We learned about perturbation theory. How if you have some existing wave function, you apply some sort of force to it and then take it away or do something to it. You mess this guy up. You mess him up here. You don't mess him up here because there's no force, and then you really mess him up here because there's a lot of force. And this is how you do it. Take first order perturbation, apply this operator into your energy integral here, using the original exact wave functions, but they're being acted on by the perturbing operator. Hartree-Fock is a perturbation theory approximation for multi-electron systems using the orbitals and the orbital interactions with these electron spatial functions. This occurs between each electron, and then this is summed You get your orbital energy. Hartree-Fock is not perfect, so it doesn't account for correlation energy.